In one of my previous videos, I completed a demonstration where I dropped a magnet through a coil of 600 turns, so this diagram to the right here. Okay, and so initially I dropped the magnet with the north pole facing downwards and it went through the coil. And at the same time I had an oscilloscope connected to the coil to measure the potential difference. And so you can see to the left here that when I dropped the coil, we started with a negative potential difference, which then shot up rapidly and then went down again. And the magnetic field of the magnet sort of stopped interfering with the coil at this point here. And so that time took approximately 198 milliseconds. Now, a few things to note is from when I initially dropped the coil to where it returns to the original potential that it had, that's approximately 3 squares that you can see there. Whereas when it rose from that point and returned to almost normal, it was only 2 squares. Now the reason for that occurring is the magnet is increasing in velocity as it's moving down due to the acceleration from gravity. Okay, so that was the first example, just dropping a magnet through a coil with the north pole facing down. And I completed the same experiment with the same coil, this time with the south pole facing down. And we can see that when I dropped the coil, it was around here somewhere. And when the magnetic field of the magnet stopped interfering with the coil, was around there. And that time is approximately the same. Okay, the only difference here is this time there was a higher potential difference first, a rapid decrease, and then a rapid increase returning to normal. And we also have that same pattern from the initial drop to where it returns to the same potential. That's it's a little over 3 squares in this case, so a bit bigger than 3 squares. And the time it took to return back to normal, well, that's around 2 squares this time as well. And once again, that's due to the magnet accelerating. And so a potential difference was generated by dropping a magnet through a coil, which is the equivalent of moving a coil through a magnetic field. And we have a name for this, which is induced EMF from a changing magnetic flux. Changing magnetic flux. Good. Now, if we remember, magnetic flux is the amount of magnetic field going through an object. Okay, and so we can define this. This is actually Faraday's law of induction. So Faraday's law of induction. Which is defined by epsilon equals negative n, so the number of coils, multiplied by the change in magnetic flux. Sometimes there's a B there next to the omega symbol, doesn't really matter too much, divided by the change in time. Okay, so where, actually I'll make that red, it's a pretty important formula for us. So where n is the number of turns in our coil, okay, the change in magnetic flux is the magnetic flux that you started with, so we'll call that omega A, take away the magnetic flux you end up with. Okay, so it's the change in magnetic flux. And then finally, delta t is just the change in time. How long did it take? So you could actually write that as t1 take t2, or t2 take t1, no difference. Change in time.